today. I've interpreted my role as basically providing a bridge between Einstein's work and David Gross's endorsement of his legacy today by filling in some of the history of how this legacy was realized, transformed, was controversial. This is obviously not going to be complete, otherwise I would have to give you a history of all of 20th century physics. It's going to be spotlights shaped by my own research and interests, and hopefully also your interests. A lot of it is based on my own work, but of course I also relied, especially in the physical cosmology part, on the work of colleagues, the work of Chris Meek, and I also had discussions very fruitful with my colleague Roberto Rani. So, and it's also shaped by my own research interests. Like David Gross, I come from particle physics, and my work in history is in the history of quantum field theory and quantum gravity. And that's also the aspect from which I'm going to address the first point here, putting symmetry first. So we already heard that Einstein's change of view was to take the transformation properties of the electromagnetic field as primary and then deduce from those the allowed dynamical laws governing. Our modern understanding of symmetry is maybe even stronger than that, than taking the transformation properties of the fields we have, the kinematical quantities we have, the entities we know to exist in nature, and then derive their dynamics from that, or constrain their dynamics from that, rather to even say we have first the pure symmetry, and then we can already deduce from that symmetry, by looking at the possible representations of that symmetry, what are even the possibilities of entities in the world? What kind of fields can we have given our initial symmetry? Which is even stronger than just saying we have the fields and their transformation properties, and from that we can deduce the dynamics. So really the symmetry sets the space of possibilities of all the fields we could possibly have, and then experiment basically fills us in as to which representations of our symmetries are really realized in nature. Now people started thinking about this when they realized the richness of the representation content of Lorentz symmetry. So in 1928, the year of the discovery of the Dirac equation, we have Charles Galton Darwin in making comments on Dirac's discovery of the Dirac equation. That up until now, relativity theory is based on nothing but the idea of invariance, as we've heard, and develops from the conception of tensors as a matter of necessity. And basically they thought, well, there's tensors, the field is one of those, we know that well, that was one of the basics for constructing special relativity. And you didn't really think about the primacy of the symmetry or of the transformation properties of the field. But then, Dirac comes along, and as Darwin remarks, it's rather disconcerting to find that apparently something has slipped through the net. So that physical quantities exist, which it would be, to say the least, very artificial and inconvenient to express as tensors, the Dirac spares. And here for the first time, you have the feeling that the symmetry really dictated, because that's what Dirac started from, of course, the symmetry dictates to you how things can transform and really gives you the space of possibilities of what kind of things you can have in the world. Now, this realization was driven home even more strongly in the following years, because of course the electron was something you had known before, and now you realize it had surprising transformation properties under the Lorentz symmetry of special relativity. But then in the ensuing years, lots of new particles that hadn't been dreamed of before were discovered or postulated. The neutron in 1932, in 1930, Pauli from the continuous spectrum of beta decay predicted the neutrino. We have here the discovery of the positron in 1932 as well, and of course the discovery of mesons attributed to be the carriers of the nuclear force initially in cosmic rays. So there was a feeling that you would be discovering lots more particles, or you could discover lots more particles, that postulating new particles was a legitimate way of doing theoretical physics. And then, of course, the question came up, what possibilities do we have to describe these particles? And that's exactly when this whole conception came up of saying, we put the symmetry first, Lorentz symmetry, we look at all of the possible representations that this theory provides us for describing particles in nature, and then we basically set the stage, and we can, from experiment or from how things fit with the interactions we want them to have, which representations we can pick to describe particles. And so in the late 30s, following these discoveries, people really worked this out, worked out the entire representation content of Lorentz theory, worked out the relativistic quantum field theories that you could make using these representations, and really developed the notion of having symmetry first, and then having the whole space of possibilities. And this was done in the late 30s, primarily by Wolfgang Pauli and his assistant Markus Fierz, who then, starting from the Lorentz symmetry, constructed quantum field theories for arbitrary spin, which could be used to describe, for example, the new particles discovered in cosmic rays. And Pauli remarked a little to Heisenberg that it seemed logically satisfying to him that in a theory in which the rest masses of particles are arbitrary, the spin should be arbitrary as well, and that he had now basically set the stage for anything that could be discovered in the future, any kind of particle, from the symmetry as the starting principle. Now, this discovery, this construction of quantum field theories for arbitrary spin leads me directly to the next point, which is dynamical space-time. Now, we've heard in David Gross's talk about the particle physicist's view of general relativity, starting from a spin-2 field, a non-geometric view, where this whole question of dynamics of space-time kind of recedes into the background part of the fun. And now, this view of general relativity as a field theory not directly related to geometry, or at least not derived from it, has its beginnings exactly in these studies of Pauli and Fierz to find all possible wave equations for new particles, for mesons and cosmic rays. And they discovered, famously in 1939, that one of the specific cases of this general possibility of quantum field theories was massless particles with spin 2. And they discovered that the equations you could derive for these particles in this framework coincided exactly with Einstein's equations for gravitational waves in general relativity in the linear approximation that he used in 1916-18. And this was, of course, just the linearized theory. Pauli already started speculating at the time that you would be able to introduce the non-linearities into this theory by looking at them not as going to higher approximations of general relativity, but rather introducing self-interactions between these spin-2 particles in exactly the same way as the non-linearities in electrodynamics and quantum electrodynamics are introduced as interaction terms between electrons and the electromagnetic field. But he didn't pursue it much further at the time because at this time quantum field theory was still a very much unsettled subject, and it was precisely the interaction terms which led to the appearance of infinities, which seemed to invalidate the entire theory and were only successfully addressed a decade later through renormalization theory. So Pauli didn't pursue that much further. And it is interesting to note that the impulse for constructing then also a theory of quantum gravity based on such a non-geometrical flat space approach came not directly or not necessarily from this spin-2 formulation, but from another formulation of gravitation in flat space that was proposed surprisingly in the same year, though there is certainly a connection. I'm talking about Nathan Rosen's 1939 theory known as his first biometric theory. And it was motivated by his desire to make general relativity more closely resemble the other, more or less successful field theories of nuclear physics, of electrodynamics. I'm saying it's not a surprise that it happened at the same time because, of course, he had been working with Einstein also on the program of the unified field theory of bringing together gravitation and electromagnetism. But it was becoming increasingly clear, and Pauli and Firtz's work is a result of this, that new field theories would have to be added to describe the nuclear interactions, and that simply bringing together gravitation and electrodynamics, as had been Einstein's goal, was not going to be sufficient, and that rather the balance was kind of tilting towards a lot of successful or less successful field theories in microscopic physics, electrodynamics, and nuclear physics, and that maybe one should go the opposite path, not do geometrization, not try to explain all other forces via geometry, as Einstein had been hoping in his unified field theory, but rather to de-geometrize gravity and make it look more like the other field theories, and thereby make it more applicable and more useful in the microscopic realm. This was, of course, really counter to Einstein's program, and he sent this paper to Einstein. I only a few days ago got the correspondence between Einstein and Rosen, this from Dennis Lehmkuhl, and Einstein tells Rosen to throw this in the wastebasket. This is silly. Rosen still goes ahead and publishes, and there's always a wavering there, whether this is just supposed to be a reformulation of GR to make it more practical, because of course Rosen introduces a second metric, that's why it's called biometric, a flat space metric, and that allows you to construct, for example, an unambiguous energy momentum tensor, which was of course important also for his thinking about gravitational waves, because he hoped thereby to somehow escape the ambiguities you got from the non-tensorial nature of the energy momentum tensor GR. So whether it was just a mathematical convenience, flat space is only introduced for convenience in the calculation, or whether one should say that the physical space-time is flat and the metric tensor of GR that one was accustomed to seeing as the tensor, the metric tensor of space-time, is not really a metric tensor, but only a gravitational tensor. So there were two metrics in Rosen's theory, and there was this ambiguity, which one is really the one describing space-time, which of course relates directly to the question in how far this theory describes the dynamics of space and time. And it was further developments of Rosen's biometric theory, especially by Papapetra in the late 40s, which were the starting point then in the 50s for the particle physicists' perturbative approach to quantizing gravity. I quote here the important work of Suraj Gupta, and we see the same wavering in his work. He starts here saying that it's really the flat space you introduce, the flat space metric, is basically your starting point in a perturbation theory. That the Minkowskian space is just a zeroth order approximation to a Riemannian space. And then by expanding all the field quantities in powers of Newton's constant, it's possible to express as expansions in the Minkowskian space. And this procedure he emphasized thereby following Rosen's first point that this was just a mathematically handy reformulation to make things work better in the newly developed renormalized perturbative quantum field theory framework. But it doesn't involve any departure from Einstein's ideas. But just like Rosen, he was wavering on this. 2 years later, he brought this approach together with a spin 2 approach from Pauli and Firtz, where it's more clear that you really start from a flat space picture and build up with an infinite number of nonlinear terms, the full Einstein equations. So he brought that together, and this wavering between whether the flat space there is really just a mathematically handy thing, or whether it really means that you're doing a flat space and thereby renouncing the Einsteinian legacy of dynamical space-time, stays with these approaches, which were then came to be known in the 50s and then in the 60s as Feynman-Gupta quantization, because Feynman was, of course, the one to most strongly popularize this flat space spin 2 approach, which he motivated by this thought experiment here. We imagine that in some small region of the universe, say a planet such as Venus, we have scientists who know all about the other 30 fields of the universe, who know just what we do about nucleons, mesons, etc., but who do not know about gravitation. And suddenly, an amazing new experiment is performed, which shows that two large neutral masses attract each other with a very, very tiny force. And then he goes on to describe how they would then have constructed the resulting field theory, describing this force in exact analogy to the nuclear forces, and would have arrived at a spin-2 formulation of the theory, thereby making it seem more natural, because a world without Einstein, without Einstein's legacy of dynamical space-time, is in a sense more probable than a world in which we have this singular appearance of Einstein building the whole thing up from the dynamics of space and time. Now, this whole flat space spin-2 approach, of course, hit a bit of a snag when it was shown to be perturbatively non-renormalizable as a starting point for quantum gravity. But of course, these debates and the ambiguity between is flat space just a mathematically handy thing here, or does it tell us something about the dynamics of space-time, still haunts modern debates about background independence and its importance. So, I'll come to my third point, physical cosmology, which is, and we heard in David Cross's lecture that, in a sense, with the application of Einstein's equations to the universe as a whole, we have for the first time this possibility of a physical cosmology, of really not doing religion or philosophy, but taking our equations as a starting point and looking at their consequences for the cosmos. But of course, the transition from philosophical cosmology to physical cosmology was not a smooth one, and its completion is, of course, still an open question whether that point has been reached, whether it can ever be reached. But it's important to see that even Einstein himself, in starting his work on physical cosmology, was willing and ready to actually modify the field equations because of philosophical considerations. That he would not start from the equations and see where they took him, but that there were strong philosophical ideas about cosmology which guided him in actually modifying the equations and proposing, of course, the famous cosmological constant. And he made it quite clear in the letter to de Sitter, a little later one than the one that was just quoted, where he said, "In my opinion, it would be rather unsatisfactory if a world without matter were possible. Rather, the metric field should be fully determined by matter and not able to exist without them. That is the core of what I mean by the requirement of the relativity of inertia. One could just as well speak of the matter conditioning geometry. To me, as long as this requirement had not yet been fulfilled, the goal of the general relativity was not yet completely achieved. This only came out with the cosmological constant." So he makes it very clear that his motivation for introducing the cosmological constant term was what can at least arguably be called a philosophical argument, what we would nowadays identify as Einstein's version of Mach's principle, namely that there is no world without matter possible. Or, in other words, as Einstein implemented it mathematically, that a single particle in an empty world should have a vanishing inertial mass, should have no inertia. That's the formulation he used, and which he used to attempt to derive the correct boundary conditions for his cosmology. That was the starting point, that the inertial mass of a test particle should go to zero as a body is taken to infinity and thereby infinitely far away from all the other masses in the world. Because the idea was that all these other masses in the world give it its inertia, and if it proceeds to infinity, there's no more mass close by to give it, to give the test body its inertia, and thus the inertial mass should vanish. This led him to these boundary conditions, at least for spatial infinity, that the metric tensor should go to this degenerate form here. But he was soon forced to see that, for several reasons, these boundary conditions are problematic. First of all, they weren't as generally covariant as he had hoped. And second of all, looking at the distant stars, it seemed that, as far as we can see, the universe is still everywhere approximately Minkowskian, and you would have to have somewhere beyond the stars that we see, suddenly the metric would have to zoom off to this singular form here by some kind of very heavy distant masses that we can't see. So he wasn't able to find boundary conditions, useful boundary conditions, that would obey Mach's principle in this form as having the inertial mass go to zero as the test body goes to infinity. And so, driven by this, he tries to get rid of boundary conditions by having a closed method, by having a closed universe where you don't have to propose boundary conditions, and where you don't even hypothetically have the chance of removing a test body to infinity and seeing its inertial mass go to zero. That just can't happen because the universe is closed. This was the guiding principle, and along with that, he took several empirically motivated conditions, namely the static universe and a homogeneous matter distribution. The latter one, which I still think is approximately accurate. The first one, of course, soon later falsified. But it was not necessarily this physical ideas, based in a sense on observation, namely the staticness of the universe, but rather the goal of implementing Mach's principle and the relativity of inertia, as he calls it, that led him to introduce the cosmological constant. And I'd also like to make the point here, of course, that the cosmological constant that he introduced was not just a free parameter, but was, in order to ensure the closedness of the universe, was actually proportional to the matter density in the universe. So it was not a free parameter that was allowed by the theory and the covariance properties, but it was really something which had to, in his mind, have a very specific value and be tied to the mass density of the universe. So this makes it, of course, a stronger blunder than if you just say that he introduced the possibility of having a cosmological constant. And this readiness to alter the dynamical equations of the theory because of philosophical considerations about how the cosmos should be, of course, because of the lack also of the experimental input, continued for many decades and shapes the debate also on steady-state cosmology, which is very strongly based on another philosophical principle, the perfect cosmological principle, that the universe should look the same at all times, because otherwise we would not be justified in extrapolating our physical laws to the past. So this transition from pre-GR cosmology to a true physical cosmology was a long one. And I'm coming to my fourth point. Unification. Now there's of course very, very much to say about this. And one could say a lot about how this as a goal has driven research, guided research, people trying to find unified field theories of all different kinds. Since there's so much to say about that, I'm going to make an entirely different point, namely how the idea that one should construct a unified field theory, that a unified field theory was in fact maybe very close, just around the corner, guided physicists in their assessment of the theories they had, of the theories that fell short of this goal of being a unified field theory. And again, I want to look at the example of early quantum field theory, where the fact that physicists thought that one should have a final unified field theory, and that was indeed at this point in the history within the range of possibilities, defined how they viewed their current theories and its difficulties. So this is Pauli remarking on quantum electrodynamics, which he had just developed together with Heisenberg in the late 1920s, saying that he was not very satisfied with Heisenberg's and his whole theory, although I do believe that it shares certain features with a future correct theory. And it was also pretty clear what that future correct theory should be, because in another letter, he outlined what the difficulties of the current quantum field theory were. These were some of the things one nowadays sees as resolved. For example, of course, the question of the infinities, which defined research of quantum field theory for the next 20 years, leading to renormalization. There's the question that the theory doesn't define whether particles are fermions or bosons, which he himself resolved with his spin statistics theorem. But the fourth major flaw of his current quantum field theory that he pointed out in the Oscar-Clyde is that we have three kinds of fields, which appear to be logically independent. The matter waves of the protons, the matter waves of the electrons, the electromagnetic field. And a unified understanding of all wave fields is, in my opinion, absolutely desirable. So, because he didn't believe that the quantum field theory they had could be the final theory, for the simple reason that it wasn't unified in this sense, people like Pauli and others were also more willing to accept the other flaws of the theory. Because of course it's going to have these difficulties with infinities, because it's not the final theory, it's not unified. We can't expect it to be a fully mathematically consistent theory. We can see that it shares certain common features with that future theory, and the goal, as long as we don't have that grand unified theory, is to extract from the imperfect theories that we have right now those features, those numerical results, where we can feel rather confident that they will coincide with what the future correct unified theory will tell us. And extracting from this imperfect theory those results that one hopes will hold up was defining for the first decades of quantum field theory, and went on even after the development of renormalization, which is normally seen to have cured the major defects of quantum field theory, removing the infinities. Even then, the acceptance of renormalization, of infinite renormalization, I should say, which is of course, which was viewed as a very makeshift procedure of getting rid of the infinities at the beginning, but that this makeshift was so readily accepted was certainly due to the fact that people had these hopes for a unified field theory in which these problems would anyway ultimately be resolved. So here's Oppenheimer at the 1948 Solvay talk, so about the time when renormalization is showing itself as a possible solution for the difficulties of quantum field theory. And he says that electrodynamics is not quite closed. That means a complete theory of which we can expect full theoretical consistency, and that's indicated not alone by the fact that for finite electron charge, the present theory is not after all self-consistent because we need infinite renormalization techniques, but equally by the existence of those small interactions with other forms of matter, to which we must in the end look for a clue, both for consistency and for the actual value of the electron's charge. So we see here the future theory in which electrodynamics is thought together with the nuclear interactions he's referring to, and then possibly also gravitation, serves as a motivation for accepting the makeshift procedures one needs to extract from the current theory the correct results. And the future theory he envisions is clearly one in the Einsteinian sense, because he thinks that it's going to fix also the free parameters of theory, which, as we just saw in David Gross's talk, was another thing that Einstein definitely expected from a future unified field. So I hope to have shown you in this brief overview how, in many different ways, Einstein's legacy has shaped physics in the ensuing decades, how it has been transformed, how the transition to viewing Einstein's legacy as the permanent thing we now see it has been a gradual process, and how also the goals set by Einstein, by their non-achievement even, have shaped the way we think about our current theories. And I'll leave it at that, and thank you very much for your attention.
Thank you very much. Well, could I ask our two speakers to take their seats up on the stage, and then we have about 20 minutes for discussion. So start there.
Thank you. So it was a great intellectual pleasure and satisfaction to listen to the previous two talks. During those talks and also during this conference, very often black holes were mentioned, information paradox, and also quantum gravity was mentioned. However, there is one result which actually has not been spelled out, so I would like to take this opportunity and do it now. So, according to loop quantum gravity, according to models of loop quantum gravity, there is certain qualitative expectation that collapsing matter, which is forming a black hole from the point of view of observer who is far from this region, actually bounces somehow in quantum way inside the black hole and then starts expanding. So the horizon which surrounds this region of bouncing is actually not what we mathematical relativity consider as absolute event horizon. This is just